Hello, everyone. Welcome back to our Demystifying Streaming Topics series. I'm Shantanu Tuli, product manager at Upsolver, and with us we have.
Hi everyone, I'm Yoni, the CTO of Upsolver.
Thanks for being here, Yoni. So I thought we could talk about data ordering for now.
Yeah, absolutely. So in our last talk, we talked about exactly once processing. And so when I'm talking about in general, when I'm talking about data correctness, so I want data to arrive correctly from my source or the events that were generated to my target. So there are two problems that I have to handle. The first is that each event should be sent once and only once. So that's the exactly once processing part. The second is that the events should arrive in order. So they should arrive in the same order that they were emitted, because applying them in the wrong order can have very weird consequences. I mean, there are a lot of business examples of that. So for example, maybe I have website tracking data, and some of my data arrives a day late. So suddenly it looks like a user is active today, but they were in fact active yesterday. It's just that the event was delayed in the pipeline somehow. I probably have an event time, so I need to now add it to aggregates that happened yesterday, but I already closed those aggregates. Those batch processes already ran. So there are a lot of things that I need to think about when data arrives late. Um, that's from the business perspective. You want to have data in a timely manner. You want all your data to arrive kind of when it's emitted, and you want to be able to do your aggregates as quickly as possible. Late data is worth less, and it can also screw up other processes. So you really want to avoid it as much as possible. But this is actually only part of the problem of data ordering. The second thing is again related to the exactly once processing. If I can't guarantee that all the data will always be processed in the same order, I am necessarily breaking the exactly once and idempotency. So if I have a process and it can process events 1, 2, 3, 4, and then the next time it's possible for it somehow, no matter how this happens, to get 1, 2, 4, 3, that just the fact that that happened means that I'm not going to have idempotent operations, which means that I'm not going to have exactly once processing. So data ordering from a technical perspective, not even from a late event arriving perspective, but just technically making sure that all my data is processed in the same order every single time is a necessity for not running into data quality issues of missing events or duplicate events. So even if I don't care about the order, I still care about the order just because of that. I'll pause for a second, and if there are any questions, or because that was a bit much, maybe.
No, I think it makes a lot of sense. Aside from the business reasons for why we would want data ordering and would at least want to know when data is arriving late so that we can adjust our pipelines accordingly, there is also just at the system level that we want to be able to process data in one order so that if we have to do it again, it stays the same. So again, going back to idempotency, which we talked about last time.
So data ordering is actually quite a hard problem. It again talks to the same issues of idempotency and exactly once. In order to guarantee data ordering, you have to guarantee that every single time you process something, you're going to process it in exactly the same way, in exactly the same order. And this kind of increases the level of difficulty because source systems are creating new data all the time. And that new data that's constantly being created kind of messes with how you're going to think about order, because it could be that I'll give a very simple example. Let's say I have two streams of data coming in, and maybe I go and I want to process a bunch of events. So I take events from the first stream and I take events from the second stream, but there are no events in the second stream. So I'll just process whatever arrived in the first stream and call it a day. Now I crash or stop processing or something, someone else comes up and tries to process it again, and then lo and behold, there is some data in the second stream. So, and maybe that data is in fact late arriving data, which should, in theory, be ordered before the data that arrived in the first stream. I wasn't aware of it before I started, but now that I am aware of it, how do I know that someone else somewhere didn't see it, so it should come after the data in the first stream, even though from the actual ordering, it should come before. So this is the kind of problems where you're running into reality. Like in order to get data ordering, I have to, in a way, predict the future, like what is going to happen or what are the boundaries that I'm willing to look at. And those need to be somehow consistent across all of my parallel processors. And that's super hard. This is a problem that isn't well solved in general in the world. There aren't very many systems that would support that, and at the same time not introduce performance bottlenecks like databases would. So first of all, again, databases solve this problem because you can begin a transaction, you can do all your stuff, can commit it, and they create a serialized order of operations. So anyone processing the database can kind of see the database as a series of transactions in order, depending on the transaction isolation level and things like that. So depending on how acid they actually are, you can kind of think of the database. And generally, most databases are implemented using a bin log. So essentially, every operation you do on the database goes into a log file that's strongly ordered. And then if you process that log file, you're going to end up with the same state that the database is in. So kind of they're solving it by serializing everything. Now, the issue with that is that it introduces a latency constraint. Like, how much data can I serialize before I start getting a backlog? Like, how many servers can do this in parallel? And then they all have to report to the same place to make sure that they get in line. So this bottleneck really constrains what a distributed system is capable of and increases cost. But I mean, generally, I mean, here we're actually talking just about size. Like, as your data volume increases, it becomes harder and harder to fulfill these constraints. And then a lot of systems, like Kafka, for example, is a very good example. They weaken the total ordering requirement, and they say, well, okay, I'm not going to order all the data because that's not feasible, and we want to be fast. Kafka's motto is kind of like, be fast. So what they're going to do is give you a total ordering per partition, and then suggest that if you want two events to be ordered, you have to make sure that they go to the same partition. But don't send too many events to the same partition because it can only handle a certain volume of events. So the way it scales is by adding partitions, but it will guarantee ordering within only a single partition. So you have to be smart about how you distribute it. Now, that's great. And so, for example, from a database replication standpoint, that's fine because I can just make sure that a primary key will always go to the same partition. And that's really all I care about as far as data ordering. But from a distributed system perspective, if I want total ordering for exactly once, that's not good enough. I have to have total ordering not only within a partition, but also between partitions to make sure that the downstream operations, as long as it's make sure the downstream operations that aren't specific to a partition will still work correctly, will still be idempotent. So this is a very hard problem, and there are solutions that are very technical that will work in most cases or work in all cases given certain constraints. But this is definitely something that that you need to think about a lot when you're designing a distributed system. And I would say that when you look at like kind of big data or data lake deployments, this is usually where you're going to run into trouble. So this is often people are kind of rolling their own and using kind of off-the-shelf open source, and they don't really address these problems very well. So you're going to have a lot of data correctness issues creep in coming from this, that you could solve it, but you need to make a lot of assumptions. You need to make a lot of add a lot of constraints, and you need to think about all the edge cases of what's going to happen if this and that to make sure that you don't end up processing data out of order.
Yeah, awesome. Thank you for explaining things, simply. I love it. All right. Well, thank you to the audience as well for sticking with us. See you next time.
Thanks a lot, everyone.